So thank you, Matthias, for the introduction. So my name is Emre. I'm from the Ruhr-Universität Bochum from Germany. And yeah, we interestingly have developed independently the same techniques against fuzzing. But I think we have a different approach on how we did it, right? Yeah, so what is the motivation? Why do we actually want to do this, right? Let's say you are someone who does not want their application to be out there and people finding bugs, right? You have a binary and you have some kind of trusted party, which is you, yourself, and your team, right? So you have your own security team who's hunting bugs. And you have also an untrusted party, which are people you do not know maybe, and from whom you don't want to find bugs, right? So if this is your goal, that they should not be able to find bugs, the question is, so how can we stop them from finding bugs, right? So the first idea you might have is to say, hey, if they can't reverse engineer my binary, they might not be able to find the bugs, right? So you might want to make that harder, so they are not able to look into your code. But in that case, the question remains, so what about automated bug finding, right? What about fuzzing? So obfuscation hinders manual reverse engineering, but if you have tools like AFL, it's still super easy. And in our paper, we have shown that most obfuscation techniques do not actually help against fuzzing, right? They will still be able to find bugs. And it's become super easy to use tools like AFL. So I had this student who never heard of AFL before, so he knew something about fuzzing, and in just one day he figured out how to use it, and then found bugs in one major online multiplayer game that's exploitable. I think even remotely, I'm not sure. So it's super easy to use, right? There are also projects like fuzzx Machina, who took the top 500 Arch Linux packages and then fuzzed them for a couple of days. And in 2 days, they found several bugs that are exploitable. So this has become super easy, right? You don't have to know much about security. So how do we impede fuzzing audits with that in mind? So what we wanted to do is get a diverse set of fuzzers and analyze them. And the idea behind that is, let's find some assumptions that fuzzers have to make necessarily, and then break these assumptions. So what we did not want to make, what we did not want to do is just target AFL specifically, right? We did not want to detect is AFL running or something like this. Let's find assumptions that fuzzers have to make, contemporary fuzzers, but also future fuzzers, and then break those assumptions so this should work universally. So this is the idea. So what we did is we compiled a list of contemporary fuzzing tools, and the ones with the black dot are the ones that we actually looked at in our evaluation. And we tried to find out assumptions, which are the columns A, B, C, and D. So we found 4 core assumptions for these fuzzers. And then we generalized them to this list of 19 fuzzers, right? So they are all based on at least one of the assumptions. And then we break them. So what are these 4 assumptions? So to come to that, I will use a demo application to demonstrate the techniques. This is a simple one where you just compare the first 3 bytes of the input to ELF, and if that's the case, you just crash, right? And if that's not the case, you print out a warning, this is not a valid ELF file, right? Okay, so what are the assumptions that we are attacking? So the first assumption is coverage yields relevant feedback. So what does that mean? You have 2 kinds of fuzzers. So in our paper, the coverage-guided fuzzer are fuzzers like AFL that use feedback, right? And there are blind fuzzers. That's the name that we chose in our paper for the ones that do not have any feedback. So both of them, they have some kind of input that they mutate, and both of them can see if a crash has happened due to this input, right? But in the case of the coverage-guided fuzzer, we can also see if there was some new coverage found. And if there was new coverage, we can add it to the queue and then mutate it again later on to find even more coverage, because by finding more coverage, you get closer to potential bugs, right? So here, the assumption is that the fuzzers had to make is that new coverage means new behavior. If you find new coverage, you found new behavior, that means you could potentially find new bugs, right? This is a reasonable assumption, nothing wrong with this assumption, it works really well, but for us, this is good to know so we can attack it. So what we did was we added, so this is a demo application with a bunch of fake branches that have some constraints that are semi-plausible, that just jump to each other, right? So if some fuzzer is observing this behavior, it sees a lot of jumping around, a lot of new code coverage. And the jumping around is based on the input. So the input is the seed for the random number generator. So you just flip one bit of the input, and it will take another pass through this maze that we introduced. So for the fuzzer, it looks like every input is interesting. Every input does something interesting. So the queue gets full of input that is actually irrelevant, but it's not obvious for the fuzzer to see that. In case of AFL, also as demonstrated earlier, the bitmap gets full. So you have so many collisions, you actually don't see anything new happening. So after you've done that, the fuzzer is actually blinded, right? It can't use its feedback mechanism in any useful way, but it can still detect crashes. So the second assumption that we had is that crashes obviously have to be observable for an outside entity, for the fuzzer. And so the idea is to just say, hey, why don't we overwrite the signals and then add our own custom signal handler that says, oh, I've seen that because you called me, a crash has happened, and I will just gracefully exit instead, right? So the outside entity just sees, oh, the application exited, so there was no crash. There are also some other techniques like detecting p-trace, because that's what HongFuzz uses or GDB uses to see that a crash has happened. So this is the one that you can actually add more stuff to it if you know that there are more techniques to detect crashes. So now your fuzzer can't use the feedback mechanism, the coverage-guided fuzzer, and also can't see any crashes. But also, there's a third assumption that we found out about, which is that you need a lot of executions per second to use fuzzing in an efficient way. So the question that we ask ourselves is, why is AFL so good at what it does? Right? So AFL is often used as a basis also in research to build your own research on top of it because it works so well. Right? So there are many reasons why it's good, but for us, one of the most important is that human knowledge is not necessary for AFL. AFL does not have to know this is this kind of application or what kind of structure the application needs. It just knows this is a binary that I need to fuzz. And coupled with that comes that AFL is just really well implemented. It's super fast. It can do thousands of executions per second, even more. And so if you have these two conditions, then you don't actually have to be smart about the code. So the thing is, as long as you are fast as AFL, as long as you can introduce mutations and check if the application found new coverage or crash, then you don't have to be smart about what you're doing. You don't have to check like, oh, this is this kind of constraint, how do I solve it? Just add more runs to it, just add more executions to it. And after a while, most of the constraints are solvable, not all of them. So how do we beat this assumption, right? So the bad approach would be to say, let's just slow down the application. So let's just add a slowdown of 100 milliseconds. You will only get 10 executions per second. But that's actually bad because in real-world scenarios, the binary that you're using will also be slowed down by 100 milliseconds. So what we ask ourselves is, how can we do a better version of this? So we still want to slow down the application, so we only get 10 executions per second or less. But what if you can do this only when being fast? Right? But the idea is here to not detect that you're being fast, right? Not check the environment like malware does, right? Not like going, oh, this is like sandbox, like this is AFL is running. Let's introduce a slowdown. But instead, do something a little bit more smart. So what we ask ourselves is, so what is the implication of being fast? Where is the difference of being fast and not being fast and used in the real world? So you know the answer because, as I said earlier, they came with the same techniques. So what we can do is, what we observed is that most input, while being fast, will be malformed, right? If you start with an empty seed, of course, most of the inputs, depending on the application, will be malformed. If you took libjpeg, for example, started with an empty seed, most of the things that you're trying at the beginning will be malformed, right? If you start with a valid JPEG file, most of the random mutations, because AFL and most fuzzers don't know anything about the application, will lead to a malformed input file. But in real-world scenarios, again, depending on the application, most inputs will be well-formed. So most JPEGs potentially that you find in the wild will be well-formed, right? So the idea here is to say, let's just slow down the application only if the input is malformed. Real-world usage of the binary will not be affected. So that's the idea. So what we have done is to say, okay, let's just go to the point where the developer already decided that, oh, this is not a valid file, and add a sleep or something that is maybe harder to detect or harder to remove, right? Some kind of slowdown. So it prints out this is not a valid ELF file, and then it introduces a sleep of 100 milliseconds, for example. So we have broken the third assumption too. So the last assumption is constraints are solvable with symbolic execution. So as you've seen earlier on the table, there were some fuzzers that built upon this assumption. Not all of them. Some fuzzers use symbolic execution. So the question is, why do they do that? Why would you use symbolic execution? As it turns out, there are some constraints that are just too hard to solve. For AFL, for example, D-word comparison, if you use plain AFL, it's just too hard to solve because you would have to guess 4 bytes of it at the same time, right? It would take a lot of execution to get that right. But for symbolic execution, this is no problem. It can just tell you, oh, these are the 4 bytes that you need to solve this constraint. So it's efficient to use it in that case. So the assumption here is that there are some constraints that are too hard to solve by random mutations alone, but symbolic executions can actually help you with that. So how do we break this assumption? We developed 2 techniques. One of the techniques is, again, similar to the fuzzification guys. We replaced constant comparison by hash comparison. Instead of saying, hey, are the 3 input bytes equal to ELF, we say, is the hash of the 3 input bytes equal to the hash of ELF, right? And the second idea that we introduced is, let's just put the input through encryption and decryption. That does actually nothing. It's the same key, it's the same output. But again, for the symbolic execution engine, now the task would be for the hash comparison to actually figure out what was the correct input to get this check to be right. And in the case of encryption and decryption, also to automatically prove that the output bytes only depend on the input bytes, right? So that nothing happened, and this is obvious. So this boggles down symbolic execution engine. It can't actually give you any results, or it would take so much time that it's not efficient anymore. So our demo application looks like this. So we get the input, put it through encryption and decryption, and then we replace the ELF comparison by their respective hash comparisons. So yeah, for the evaluation, so the most part of this paper was doing the evaluation, right? One of the things that we did is we used a very simple example, a dummy application that just checks 4 different bytes if they're correct. And if they're correct, it just crashes. So the idea was, if we can protect this application, this very simple application, from fuzzers, then every more difficult, more complex application will also be protected. And as we can see here, the fuzzers that we evaluated this on, the assumptions that we broke actually apply specifically to those fuzzers that have this assumption, right? That rely on this assumption. And we executed them all for 24 hours, so they did not find the very easy bug that was that they were able to find in seconds or minutes before on the plain binary. And now with AntiFuzz, they are not able to find any bugs. And then we activated all of the features and let it run for 100 hours, and still they were unable to find any bugs, to observe anything. And to yeah, so you might think that, yeah, okay, if you mask every bug, if you just hide the bugs, of course you won't see any bugs, right? So we wanted also to demonstrate that this is not just about hiding the bug, but also to impeding fuzzing audits, right? So we let it run for 24 hours, 3 runs each, and this is one of the examples for bin utils, for object dump. And you can see that on the plain binary, it finds a lot of coverage in 24 hours, the 4 fuzzers that we looked at. But when you protect the application with AntiFuzz, it barely finds more than the baseline, right? So all the low-hanging fruit that you find in the beginning that are too easy to find, those are the ones that you can actually find. So fuzzing attempts are actually really impeded by this. So to conclude this talk, so what we did was we had a systematic analysis of a diverse set of fuzzers, and we found 4 core assumptions that they rely on, in the hope that other fuzzers in the future would also rely on this assumption. So we can just break the assumptions now, and hopefully all the other fuzzers that we do not know about will also be broken. So these are the 4, right? Break coverage-guided fuzzing, just hide the bugs that are still being found, and then just slow down the fuzzing attempt, but not in real-world cases, and also boggle down any symbolic execution attempts. So this is what AntiFuzz does, and we implemented it in a Python script that generates a C header file that you can include into your project. And you can find it here on our Ruhr-Universität page. You can play around with it. So thank you for your attention. Any questions?
Questions?
Oh yeah, sure. Sorry.
Are you going to ask the same question?
No, I like this one. So for your input manipulation, where you're looking for what's considered a valid input and invalid input,
Yeah.
I'm assuming you're looking at the program checks to kind of verify that.
So let me say, and at this point, this is all manually added by the developer.
Oh, okay.
So so the fuzzification guys did the automatic finding of this. So we did not do this. We said so the developer knows where the path is, where the file is malformed. It just adds a line of code.
Okay. Right. Have you put any thought into what type of file formats or input formats would not really this wouldn't be applicable to?
Yeah. So actually the one that I showed, the object dump, it actually accepts a lot of valid things, right? So when we added the slowdown to this, so most of the times it did not do anything. So I could see the AFL output, and it actually could still do hundreds or thousands of executions, right? So I think there are some programs that do not have any kind of structure, where it's not important. So in those cases, it does not work. But a lot of applications, we did not do any evaluation on which applications in particular, but I think most applications will have some kind of detection of malformed input.
Okay, cool. Yeah. Thank you.
Thank you.
Hi, thanks for a nice talk. I'm Mohammed from UC Irvine. My question is that did you evaluate the effect of your work on normal execution of the program?
So we had, on the paper, we had some evaluation on the overhead introduced. So we protected the application with AntiFuzz, and then we evaluated what the overhead was on that application. Right.
So do you have a number now about the average?
I think it was so small that we couldn't measure it. So it's a really small number.
Great, thanks.
Yeah, no problem.
Advertisements?
No. So one question I had is, if you're relying on adding these delays to uncommon paths, then if this is like a server application, does this mean that if I can make your server hit an uncommon path reliably, I can cause a denial of service?
This is a really good point. I should have mentioned that. So of course, as a developer, you should decide when to introduce these techniques or not. And server application is a perfect example where you should not do this, right? So any kind of performance critical application, you should not do any kind of slowdown. But a really good question. Thank you.
I also wondered that as an attacker, could you knob out individual locations that you find that slow down the fuzzing, or use some form of grammar-based approach where you only constrain the mutation to a certain part of the program where it is valid, so that you get past all of these checks and then can still find different kinds of vulnerabilities deeper into the program? Yeah.
So in our case, in AntiFuzz, it's super easy to remove. So in our paper, what we actually said was that if you are using AntiFuzz, you're probably also using obfuscation, and you should, right? You add AntiFuzz, and then you add obfuscation on top. So this is not easy to remove. So if you look just on a binary that is protected by AntiFuzz, you will see the 10,000 of fake edges that you introduce, right? It's super easy to remove. So add obfuscation, and then it's all based on the security of the obfuscation.
Perfect. Any other questions? Otherwise, let's thank Emre again.
Thank you.